Okay, in this video we're going to talk about how we can calculate the volumes of gases. And if you look at this statement here, 1 mole of any gas, doesn't matter what gas it is, occupies 24 dm cubed. If you have 1 mole of it, and that's at 25 degrees C in standard pressure. Okay, so we can sort of put that into a little equation, if you like, this one here. So if you want to convert the volumes of gases and moles, volume is equal to moles times 24, or if you prefer the triangle, there you've got that. Now, just a quick word of warning here is don't confuse. This is to only be used for gases, not when you're talking about solutions and stuff, which some people get a bit confused sometimes, just for gases. Okay, so that may seem, the fact that it doesn't matter what the gas is, occupies the same volume, may seem quite strange. So let's think about carbon dioxide. What is the mass of 1 mole of carbon dioxide? Well, we can use this equation here, and we know that mass is equal to moles multiplied by the mR. Right, so the number of how many moles of carbon dioxide we've got 1, and the mR is 44. So the mass we've got is 44 grams. So 1 mole of carbon dioxide weighs 44 grams. Let's think we do the same for hydrogen. So the mass of 1 mole of hydrogen, well, what we have to do is equal to the number of moles, which is 1. We've got 1 mole of hydrogen multiplied by the mR of hydrogen, well, that's 2. So that only weighs 2 grams. So 2 grams of hydrogen take up the same amount of volume as 44 grams of carbon dioxide. Now, how come it doesn't really seem to matter the size of the molecule, how much space it takes up? Well, we can maybe have a little think about that. So I'm just going to draw a box, and this box is so that's a cube of 24 dm cubed. Okay, I've got another one here, and I'm going to do it for CO2. I should put in, right, 6 times 10 to the 23 molecules of CO2. I'm only going to draw 5 because it takes too long to draw that many. And we've got to remember they're flying around all over the place. Right, now the actual space that the carbon dioxide molecule takes up is all intents and purposes, it's 0. And the space that the that the carbon dioxide molecule takes up is due to the fact that it's flying around all over the place. It's not due to the volume of the molecule itself. So it doesn't really matter how big. So here's our hydrogen molecules, and there's just 5 of them there. They're smaller, a lot smaller than carbon dioxide, and a lot lighter, but they'd still take up the same space. Okay, flying around everywhere. Right, let's have a look. Just have a look. So I've got 4 balloons, and these balloons all have a volume of 24 dm cubed, so they're pretty big balloons. I've filled this one up with hydrogen. That only weighs 2 grams. I fill this one up with helium. Well, the mR of helium is 4. That weighs 4 grams. That's twice as heavy. Oxygen weighs 32, and the carbon dioxide weighs 44 grams. So that explains why if you get a balloon filled up with helium or hydrogen, it's got a very low density, because 1 mole takes up 24 dm cubed, but in the case of hydrogen, it only weighs 2 grams. It's much less dense than air, so it will float up. Whereas carbon dioxide is heavier than air. So that's going to sink. The carbon dioxide balloon will sink. Right, let's do some calculations involving reacting masses and stuff then, and gas volumes. So this is, you need to be able to do reacting mass calculations to do this bit. It's combining 2 things. So the question is, what volume of nitrogen dioxide gas, which is a brown gas, is produced when, let's say, 16.0 grams of magnesium nitrate undergoes thermal decomposition. So I need the equation. We've got magnesium nitrate heat it up, it will form magnesium oxide, solid. This is a solid as well. Nitrogen dioxide gas, and it will also make oxygen gas. Now, to make that balance, I need to put a 2 in front of that, which means I'm going to make 2 moles of magnesium oxide, 4 moles of NO2 gas, and 1 mole of O2. So what 2 things are we interested in? We're interested in the moles of magnesium nitrate and the moles of nitrogen dioxide. So we can see here that 2 moles of this will give us 4 moles of NO2. So I'm going to simplify that. 1 mole of magnesium nitrate is going to give us 2 moles of that. Okay, now I'm going to grab hold of our moles mass equation. I'll just write it down again. So moles is equal to mass over mR. So how many moles of magnesium nitrate have we got in 16 grams? So moles of magnesium nitrate is equal to the mass, 16, over the mR of magnesium nitrate, so that's going to be 24 for the magnesium. You've got 2 nitrogens, so that's 2 times 14 for the nitrogens. And you have got 6 oxygens, so that's 6 times 16. And that is 148, okay? So the moles, 16 divided by the 148, that's 0.108. So if we have 0.108 moles of magnesium nitrate, we are going to make double the moles of NO2, because look, we've got 2 moles of that. So that's going to be 0.216. So we're going to make that many moles of, let's write it down. We make 0.216 moles of NO2. What volume is that going to occupy? Well, volume of a gas is equal to the number of moles multiplied by 24 from the equation at the top before, and that volume is going to be in dm cubed. So the volume is going to be equal to 0.216 times 24. That's going to be equal to 5.184 dm cubed. If you prefer that in centimeters cubed, multiplied by 1,000, 5,184 centimeters cubed of nitrogen dioxide gas. So that's combining the two, the reacting mass calculations and these new gas calculations. Right, now if you want to do some more of those, there's a few examples down here. Here they are, with the answers, if you want to try those yourself. Okay, so in each case you get an equation. Which you need because it's a reacting mass calculation, and you've got to work out the volume of gas produced. Okay, I'll leave that there.